So start. And today we are going to start fresh chapter. Okay. Theories of failure, or we can say theories of elastic failure. Theories of elastic failures. There are many failures theories are there, but we are in our syllabus. It's only elastic theory. There's again brittle is there, fracture mechanics is there, where you can study the fracture mechanics and you can understand that failure behaviors. So there are many theories of. So this is theories of failure. Before that, as you know, when you are going to, let's say, this is my stress, this is strain, right? When we are going to draw, let's say, mild steel, I'm saying right now, okay? And if we are going to draw, this is our fracture point, right? Here, our yield point is there, lower yield point, and this is our ultimate point, right? This is plastic region. So whenever after your 0 a b, b is your elastic point, a is your limit of proportionality, means whenever you are going to remove the load, it will regain its original shape and size. When it will reach to elastic point, it will not. Whenever, what we are saying, what we know up to now, what we know, a material, what I am saying, a material is said to be failed. Means now we are going for a failure point. Okay. If elastic limit is exceeded, so whenever elastic limit exceeds, so what we are saying, it is going for your failure, or you can say permanent deformation take place. Means there will be deformation, so it will, the original shape and size, whatever the original shape and size is there, it will not be there. Okay, it is going to take place. Okay, what does this mean? This means, see, after elastic limit is reached, when the elastic limit reached, okay, or when material start yielding. Okay, what I'm saying, material start yield behavior, you understood. I always told you that you will find out yield means the whenever you will load your bars. Okay, so at the yield point you will check the bars, there will be, you know, change in your material. Wherever you will find the change of your material, that time it is yielding. Okay, so yielding. Now another point is, in tension test, yield stress. Okay, for mild steel it is clearly known. If it will not be mild steel, you will draw the proof stress, and wherever it is going to cut, that is your proof strain, and wherever it is going to cut, that is your proof stress, right? That we called it as design stress for any material. Okay, so can be easily determined, easily determined, but if member is subjected to various complex stresses, then it is very difficult. If I am saying, okay, I am applying a load, there will not be any, any other load is not going to take place. Means other stresses are not there. Only your loading stresses is there. What you are applying a load, and any other load is not there. So that time it is very easy. Why? Your load you applied, other parameter you are not considering, and with that load you can understand what is going on with your material, right? So then it is very difficult to know the point of yielding. Means when if complex stresses, means there are many stresses are applied over at the same time, like bending, okay, then your normal direct stresses are there, bending stresses are there. If there are a shear stress, means types of stresses if going to increase, okay, so yielding or fracture is going to occur. Okay, yielding or fracture. So why we should know this? Okay, any problem up to here? So why we require that? So why we required to do this? We should know the theories of means failure. So to improve, whenever you will find out your static loading, dynamic loading, whenever your failure occurs, so best part is to do your stress strain analysis. Okay, so through that you can any design component you are doing, any beam elements or any structural elements of your, let it be for your vehicle, let it be for your machinery parts, or any, I'm saying let it be for your buildings or anywhere. Okay, when you will know, you can improve, have to improve the designs of machine components. Okay, and various, after that, you can, many examples are there, not only to improve design machine components, you can design your structural elements also. So you can, for civil you can say structural element, or mechanical machine components. So okay, so like that. So now there are various theories are there. What I am saying, there are various theories are there. Whenever we saying theories, remember, in a very simple laws, theories, someone knows something that is coming from past. Okay, that theory is given by someone, and that only we are learning. Okay, it is given by someone, we are learning that. It is very simple, I am saying. Okay, means someone given some knowledge in the past, he understood that knowledge, he wrote that knowledge we are going to transfer over here. Okay, so whenever you applications part will be different. So various theories of failure are developed by are developed considering physical behavior of material. So physical behavior of material means we are not saying chemically, thermally. Okay, physiochemiothermal means physical, thermal, and your, this is your mechanical also you can say. I am saying physical, chemical, thermal. All three you will consider, it will be different scenario. So here only physical behavior we are understanding. Okay. So there are two types of two types modes of failure. Very simple. First, either you say yielding or you can say ductile failure. Okay, ductile failure. Second, brittle failure, brittle, or fracture failure. Okay, so yes. Any questions? Why we are understanding the theory of failure? Is clear? Now the first theory is your maximum principal stress theory. As name itself is saying something, so try to understand from that also sometimes. Okay, and this is given by Rankine. It is also called as Rankine's theory. So sometimes they can ask you in the objective, so you should remember the name also. Okay. So what this theory is saying? Okay, according to this theory, according to this theory, the material or your elements subjected to complex stresses will fail when principal stresses induced in material reaches to yield stress. Okay, means sigma 1 equal to sigma y in your tension. Okay, means the stress is reaching to your yield point. Okay, so and failure occur in compression when principal when least principal stresses sigma 3 reaches the elastic limit stress, the elastic limit stress, or you can say simply yield stress. Means your materials yield stress you will get to know from tension test, right? So from tension test you will understand your yield stress, what will be the yield stress. Okay, and you for your mild steel you know that, right? What it is for mild steel? Mild steel yield stress. So your sigma 3 will be equal to sigma y for compression. Anyone mild steel?
So 250 MBA.
Okay. So now you understood the sigma 1 will be, this will be in tension, this will be in compression. When it is going to reach to yield stress, that can, it is going to be an failure. Okay. So if I am saying that if it should not, means according to this theory, for no failure, according to this theory, for no failure, maximum principal stresses, maximum principal stress is, should be, this is maximum principal, should be less than to your yield stress. Okay. And for your design stress, for design stress, okay, whenever you are going to design any component, any element, okay, so you have to go for design stress, not for your yield stress. Yield is your where the material is going to fail. So we are not going for that failure point where material is going to fail. Then we are going to understand whatever the failure pattern is there. No, we'll consider some factor of safety, means we are not applying 250 MPa. We will apply below that. We will include, let's say, two factor of safety. If I am going to include, so 250 divided by 2, that is 125 MPa. So I am limiting my material to go up to 125 MPa. It can go little bit beyond and below, but your material will be safe always. So generally, whenever you are designing a material, you will go for a safer side. Okay. So right now, I know you people are stressed when you are preparing gate exams and all, right? As gate exam is over, you will be in your comfortable position, right? So when your comfort level comes, whatever you want to do in your leisure time, you will do, right? So it is like that. Suitable factor of safety is introduced. So why we are applying that is called your design stress, means we are not applying fully one day, you can say design stress, you can say D also, design stress, that will be less than equal to, this will be sigma y by factor of safety. Whatever factor of safety is there, the design stress should be less than equal to. And remember one point over here. Remember, it is well suited for brittle material. So whenever brittle material is there, this theory is suitable. So this is called your concrete. You can say any other, you can material, brittle material. You can in your uh, glass, like that. Whichever the brittle material is there, that. Not, I am not saying nowadays. There are composite materials are there. So don't include the composite material, because as the composite, itself, uh, name, from the name itself you can see composite means there will be mixture of two materials. Okay, so that time the material, obviously, see, whenever we are mixing any two materials, we are going to mix what, which is one will be in good intention, one will be good, good in compression. So mixture of tension and compression we are going to do in your any case. I am saying, let it be any, I am saying that not only mechanical engineering, not only civil engineering, I am saying You consider in a broad sense. Okay. Now, next part. One more point over here. If your yield stress in tension equal to yield stress in compression, okay, then this theory may be represented graphically. Graphical. That you can consider, see over here. Okay, this is your sigma 2, this is your sigma 1. So that is your yield stress. Now sigma y I can write here sigma 1, sigma y, here sigma y, sigma 2, right? Or sigma yield stress you can apply. So one more point over here, failure, okay, will take place if any point having coordinate in the system, and wherever it is going to take place, sigma 1 minus sigma 1 comma sigma 2 falls outside the failure envelope, or you can say plane also. Now, limitations. This is important. Okay, limitations. Why important? We should know what theory limits to. Whenever there is a limitation, means they are neglecting something. So this theory neglect the effect of minor and intermediate mediate principal stresses. Okay, this theory is not suitable for this theory is not suitable for ductile material. You should remember this point. Okay, which is not suitable. You should always mark like that. And again, this theory result of this theory are not suitable during hydrostatic loading. Means inside your water, whenever the forces are going to come over there, so there it is not applicable. And when the material is subjected to pure shear, results for ductile material for ductile material are unsafe or not safe. Okay, so you will check this how it is going to be. See, when it is going to be your pure shear, you know it is going to be like this. Your element is going to be okay. There will be complementary stresses over this side. So tau max. So sigma 1 is going to be in that case when it is going to be your only shear condition, means that time it will be tau max and sigma 2 will be minus tau max. Okay, correct. So according to this theory, what is this theory saying? According to this theory, okay, sigma 1 should be less than equal to your yield stress, right? So tau max, in this case, tau max should be less than equal to your yield strength. Okay, but when we did experiments, okay, but from the experimental results, okay, shows shows failure occurs much much earlier. Okay, that is uh, as per your experimental results. Okay, so that will be tau max equal to 0.57 of sigma y. So for no failure in ductile material under a pure shear, tau max should be tau max less than equal to 0.57 of your yield strength. Okay, this is as per your experimental result. So this theory says it should be this, but as per experimental result, this is your case. Okay, so you should remember these points. Any questions? No. Write down the question according to your maximum principal stress theory. Okay, so the limit of proportionality of a certain steel Uh, Hello, I'm audible?
Yes, sir.
Yes. Now, the limit of proportionality,
Sir, but you cannot be seen.
screen is not visible.
No, sir. Now it's
Hmm. Yes, now we are good to go. Certain steel sample is 300 MPa. In simple tension test, it is subjected. It is subjected to principal stresses of 150 MPa in tension and 60 MPa again tensile and 30 MPa 40 MPa tensile. According to according to maximum principal stress theory, the factor of safety in this case would be A 10, B 5, C 4, D 2. Now we'll write down what is your yield. Yield strength is given 300 MPa. Then your sigma 1 150, sigma 2 60, sigma 3 30, all are in MPa and positive. Now, according to maximum stress theory and Rankine's theory, what? Remember, write down Rankine's theory. Sometimes they will ask the question in government examination in gate also there will be a match the following for 2 marks question. So they will write down the scientist or theory's name. Okay. So what this theory says, sigma 1 is less than equal to your yield strength, right? Then as yield strength comes, okay, that will be your sigma 3 or no, sigma 1 is less than equal to your yield strength divided by factor of safety. They are asking us factor of safety, and sigma 1 is 150, and that is 300 divided by factor of safety. So factor of safety should be less than equal to 300 divided by 150. That is factor of safety is equal to 2. Correct. So your answer is B. Any question? Easy, right? One more. Okay. Question. A prismatic circular bar is subjected to a pull of 100 kilonewton and transverse shear of 45 kilonewton using maximum principal stress theory, determine the dia of bar, and your yield strength is given over here 300 MPa, and factor of safety it is given 300. Okay, and this bar is given to you, and over here 100 kilonewton. Okay, if you are going to draw the stress diagram, it will be like this, right? And at the center there will be your tau max. Here tau will be equal to 0. This side also tau will be equal to 0, and this side your transverse force is going to act, that is 45 kilonewton. Okay, so now we'll consider a point over it. A minute. Yes. You can try also. Now, if you are considering a point where consider, okay, point. Now, if I consider a point, and over here, your sigma z stress is going to act here, sigma z, and this is going to be your stress shear, right? Now, this is your x direction, this is your y direction, right? Now, solution, the normal stress and shear stress at point P is equal to, how you are going to calculate normal stress, sigma z is equal to force by area. What is your force applied? 100 kilonewton. P by 8. What is P over here? That is 100 into 10 raised to power 3, and pi d square by 4, and they are asking us d square, so keep it like that only. Okay, and so your sigma z will be equal to 127.32 into 10 raised to power 3 divided by d square. Okay, this is our relation now with stress and diameter. Okay, now, and in your, see, in two direction they given us, one in this 100 kilonewton, that is your x direction, right? So this is your x direction, and the sigma y means in y direction there is no stresses, so 0. Okay, so shear stress, now shear stress at the point now in circular section, the tau max, what is tau for circular section? That is 4 by 3 of tau average, correct? That is 4 by 3, that is multiplied by the shear force by area, right? So that will be equal to 4 by 3 into shear forces 45 into 10 raised to power 3 kilonewton, that is in Newton, and divide by pi d square by 4. D you keep it like that, calculate, that is going to come around 76.39 into 10 raised to power 3 by d by square. Now over here, when what according to maximum principal case stress theory, we require principal stresses, right? So now we will find out the principal stresses. Now P point, now your P point is subjected to, now point P can be considered as stress element subjected to stress in x direction and tau, right? So major principal stress may be given as, yes, the formula is sigma 1 is equal to sigma x plus sigma y divided by 2, right? Plus under root sigma x minus sigma y divided by 2 square plus tau square. So just you have to place your values, right? Just place that values, that is sigma 1 will be equal to 127.32 into 10 raised to power 3 divided by 2 into d square plus under root 127.32 into 10 raised to power 3 minus 0, and you are divide by 2 into d square whole square divide by plus 76.39 into 10 raised to power 3 d square raised to power square. Okay, now so to the, you can cancel over here, that will be 63.66 into 10 raised to power 3 divided by d square plus, again you can do over here also, that is under root of 63.66 into 10 raised to power 3 divided by d square whole square plus 76.39 into 10 raised to power 3 divided by d square whole square, correct? Now next step, what we are going to do, we are taking the, you can take the squares off and you can calculate, that is going to be 63.66 divided by d square into 10 raised to power 3. Here you can take 10 raised to power 3 out common, and whatever left is you can calculate, that is 99.43 by d square into 10 raised to power 3. Again you can take here 10 raised to 3 common, it is 163.09 into 10 raised to power 3 divided by d square. Okay, that is your sigma 1. Now according to maximum principal stress theory, or Rankine's theory, what we can say is sigma 1 is less than equal to sigma y by factor of safety, and your factor of safety is given to you. Sigma 1 is, you know, that is sigma 1 less than equal to sigma 1 we know, right? We'll write down sigma 1 163.09 into 10 raised to power 3 divided by t square. Okay, and your yield is 300 divided by 3. Okay, so 300, and so your d square greater than equal to 163.09 into 10 raised to power 3 divided by 100. 110, only 10. So d square is greater than equal to 1630.90. Take square root and you will find out d will be equal to 40.38 mm. Yes, any questions you can ask? So easy maximum principal stress theory, right? Next theory is maximum principal strain. Okay. What? Maximum principal strain theory, and this is given by Saint Venet theory. See, according to this theory, a minute. Sorry. Now, according to this theory, okay, failure occurs when maximum strain or principal strain. Again, it is like, principal strain, how it is your principal stress, according to that principal strain in the complex stress system. Okay, to the yield strain, to the yield strain under uniaxial loading. Uni means single. Uniaxial loading. Okay, so now principal strain is sigma 1, that is equal to your yield strain, right? So now where you know how apply your applications of Hooke's law, that is strain is equal to sigma 1 by E minus mu times of sigma 2 by E minus mu times of sigma 3 by E. So your strain in y direction will be simply sigma y by E. What is strain? What is stress? Stress is directly proportional to strain, and when you will remove your proportionality, you will get your Young's modulus, right? So strain is sigma y by E yield strength. So can I write down when sigma your strain principal strain is equal to, for means your no failure condition or no failure condition. Okay, so sigma 1 will be less than equal to your yield strain. Okay, and that time the strain in will be sigma y by e. Okay, and for design purpose, for design, okay, that strain will be less than equal to sigma p by e, where what is sigma p over here? Permissible stress. Permissible stress. And how you can calculate permissible stress? Sigma y will be equal to sigma y upon factor of safety. Okay, and when you are going to check the this angle, okay, with this angle, that will be at 45 degrees. Strain is in sigma 1 and sigma 2. This is at 45 degree. This is called your shear diagonal, where your strain can be, principal strain can occur. Okay, and again this theory can be applied for ductile, and brittle material both, but not accurate for either cases. Not accurate for either case. Uh, Again, there are limitations. Okay, so we'll go to limitation now. Limitations. Okay, where it is going to say it is not going to work, right? So in hydrostatic loading, the results are not accurate. So again, don't apply to hydrostatic condition. Then in case of pure shear, okay, results are unsafe, not safe for ductile material, but better than maximum principal stress theory. Okay, that is Saint Mian principle. And over here, when it is going to be in pure shear condition, okay, when it is going to be in a pure shear condition, so how it is going to behave in this state? So sigma 1 again, that will be tau max, sigma 2 will be minus tau max. So according to this theory, strain is less than equal to your yield by modulus of elasticity. Now there is only in two direction, because 2D we are considering. So sigma 1, apply your applications of Hooke law, sigma 1 minus mu times of sigma 2 by E less than equal to sigma y by E, because we are not taking any 3D condition. So E will get cancelled. So sigma 1 minus mu times of sigma 2 less than equal to yield strength, right? Now already you know sigma 1 is tau max minus mu times minus tau max less than equal to yield stress, right? So in this case, this minus minus plus, so tau max into 1 plus mu, that is less than equal to your sigma y. So sigma y divided by, so tau max less than equal to your sigma y by plus mu, right? What is mu for ductile materials? For ductile metals, generally it will range from your, it will be zero point 0.3, 0.23, 0.24 like that, and zero point 0.2 to zero point 0.3. Okay, you can consider. So mu is 0.3, just assuming. Okay, so we'll put over here. So that will be tau max will be equal to less than equal to 0.77 sigma y, which is still unsafe or not safe, right? You can understand from here. I think time is over. Yes. Thank you.